Hi, everyone. It is Mrs. Moody. I'm sorry I sound a little off today. My 3-year-old decided to give me a cold for Thanksgiving. So I apologize in advance if there is a lot of coughing and if you can't understand me as well as usual because my voice is a little raspy. So if anyone decides to come into the live lesson, then I will let them in, and hopefully there will be so that we could get some questions later on. But I'm going to go ahead and start. Today, the live lesson is going to be on scientific notation. And the reason that I decided to do this live lesson on scientific notation, which is 106 and 107, is because I have started to notice a lot of people having confusion on scientific notation, especially operations with scientific notation, that 1.07. So the way I explain scientific notation tends to be a little different, as most things are, than the traditional way of explaining it. So I have put together a really lovely PowerPoint that I am going to uh, share with you. And if people have questions after that, then we will go over them. So this is scientific notation. All right. Let's see. There we go. Okay. So scientific notation is all about place value. Okay. A lot of people get confused because it doesn't look like place value, but it really is. It's all about place value. So when we are looking at the pattern of multiplying or dividing by 10, we're talking about place values because we use a base 10 system. There's other systems. Sure, the binary systems is what computers are based on. There are base 12 systems. And one of the things you learn when you get into Algebra 2 and beyond is how to work in base 10, things that are not base 10 systems using something called logarithms. And, just in case you are interested in what that is, it is called, oops, not that, this. Logarithms or logs. So nothing to do with this particular lesson. I mean, very, very loosely. But anyway, that's because we live in a base 10 system. Now, what does that mean for scientific notation? Well, because we live in a base 10 system, when you get to 10 of a place value, we regroup and we create a new place value. So if I have 10 pennies or 10 ones, then I can exchange that for a dime or 110. If I have 10 dimes or 10 tens, I can exchange that for $1. Or if I have 100 pennies or 100 ones, I can exchange that for $1. So when we're talking about powers of 10, that's what we're talking about. Is we're talking about adding a place value or subtracting a place value, depending on multiplying or dividing. And that's really just regrouping when we multiply and divide. So that is why when you're multiplying by a power of 10, 10, 100, 1000, the decimal moves to the right because you are forcing this sort of regroup. You're multiplying by a power of 10. So you're adding that place value. So it tells us how many place values to add. 10 is one place value, 100 is two place values, and so on and so on. Dividing is just the opposite. We're removing place values because we're dividing by power of 10. So we're going from, hundreds to tens to ones to tenths, et cetera, et cetera. You have to know your place values. If you're not confident in your place values, that is something that you really have to spend time on. You've got to know your place values. And here's something else that I will spend some more time on in a different lesson. I did a module 1 review, but I didn't spend a whole lot of time on this. Negative exponents. Consistently, I see people think of negative exponents as negative numbers. Negative exponents are not negative numbers. They're not. They are a way we show division. It's a lazy person's way to write a fraction. And there's nothing wrong with being lazy as long as it's not costing you anything you don't want to pay, which negative exponents doesn't cost me anything. So I'm fine writing negative exponents. Now, what does scientific notation do? So scientific notation is just an abbreviation for a number. It's no different than any abbreviations we use in our daily life. It doesn't mean anything by itself. It stands for something. Okay, so when I have a number times a power of 10, that power of 10 tells me what I have to do to get the actual value of the number. So it's like a instruction manual. So I have 3.1 times 10 to the fifth. That 10 to the fifth is directions. It tells me I have to multiply the number I'm given, 3.1, by the power of 10, which is 100,000. That's 10 times 10 times 10 times 10 times 10. And that will give me the number's actual value. Because if I multiply 3.1 times 100,000, I get the actual value of the number. If I worked it out with, by hand. And if I have a negative exponent, again, that means divide. So here I would have to divide by 1,000 in order to see what the value of the number actually is. So scientific notation doesn't give us the true value. Scientific notation gives us directions for how to get the true value of the number. Because of that, we can write numbers any way we want to. And that's really what math is about. Math is about rewriting things in different ways to achieve different goals. It all comes down to that. It all comes down to, can you rewrite something in a way that gets you what you want? That's it. So we can rewrite numbers with powers of 10, and as long as we don't change what the number is really worth or its value, that's totally fine. So let's take this for example. Okay. So we have, hang on, I'm going to cross this out for a second. Don't look at this right now. Well, that's not very dark. Okay, that's totally not working the way I thought it would. Okay, well, just don't look at this right now. Okay, that's probably like more distracting than anything, so I'm just gonna leave that. So anyway, let's take this for example. All right, so we have this number, 3,741. I just want to rewrite it. 3,741, I can rewrite that as 374.1 or 1/10 times 10 to the first power. Because if I do that, what that really means is 374 1 times 10. Well, that just gives me this extra place value right here. When I do 0 times this, 0 times this, 0 times this, all it does, I'm not writing it in a good way. All it does is gives us an extra place value. So 0 times 1, 0 times 4, 0 times 7, 0 times 3, and then everything times 1. So 10 times 1 is 10, and then 4, 7, 3. Or you probably were taught that you just have to put this little like placeholder here. And that's really why, because you're multiplying by 10. And so then look, we have this extra place value. That's what this extra place value comes from. That's where it comes from, is right here. And that's how we get this number to this number, for going from here back to here. It's all about, how do I get back to the place I started? Well, where I started, the value of the number, the only way to get back to it, if I have this number, okay, sorry, if I start here, but then I come this way, in order to get back to the way I started, I have to multiply by a power of 10 because I took away a place value. And now I want to add that place value back in order to get to my original number. Same thing with this over here. Okay, 37.41. So I had 3,741. I still have it. I didn't change that. I have 3,741. And then I said, you know what? I want to rewrite this. I'm not changing it. It's the same number. It's worth the same amount. But I'm going to remove two place values. So I'm going to divide by 100. And that gives me this. And then now that I'm here, I'm going to go back to my original number. Well, that means I'm going to have to multiply by 100 because I took two place values away. Now I want to add them back. So I multiply by 100 and I get back my original number. Same thing here. Here I took away three place values in order to get back to my original value, my whole value. I need to multiply by three place values. Here I took four place values away. Then I need to multiply or give four place values back in order to get back to my true value. Yay. All right. Okay, so when we talk about scientific notation, it's still just an abbreviation with a power of 10. We've just rewritten a number, but it's a very specific type of abbreviation. It's very special. And the reason it's special is because it has rules. So the number that you're multiplying by your power of 10 has to be within 1 and less than 10. Okay. This makes sense because if you have a power of 10, then it becomes a new place value. So the definition of scientific notation is that you can only be working up to very like right before the place value of tens, like 9.9999999 forever and ever and ever, repeating decimal. You can't hit 10 because if you hit 10, then you're in a new place value. And the whole point of scientific notation, that abbreviation, is that you're dealing with something in the ones place and then you manipulate it with your powers of 10. Okay. So that's why scientific notation is very specific. And this is how we sort of define scientific notation. We say scientific notation is a number that is greater than or equal to 1, but less than 9, less than 10. This should say 10. This should say 10. I'll fix that when I post it. No, I won't because it's going to be in the video. So that should say 10. Then 10 times 10 to a power. And you can use whatever variables you want, but that's scientific notation where you have some number that's greater than or equal to 1, but less than 10 times 10 to some power. Because if you multiply it by that power of 10, it gives you the true value of the number. Because right now it's just an expression. But if we turned it into an equation, you would get the true value. Let me clear this. There we go. So that's the basic rundown of what scientific notation is. Now, we have to be able to use scientific notation. The whole point of scientific notation is to use it, which, if you grow up to be I don't know, anything that doesn't use scientific notation. So scientific notation is really popular in like engineering, sciences, that, mathematical fields, that kind of stuff, where you have really big numbers, really small numbers. So if you go into anything that isn't that, basically, you become an artist, you become a writer, you become, I don't know, a pro football player, like my son wants to be. You aren't going to use scientific notation on a very consistent basis, and that's okay. But some people will, and so it's useful if you can add and subtract, multiply and divide with scientific notation. It's exactly like regular subtracting and adding. When you learn how to add and subtract things that have multiple place values, you have to be able to line the place values up, because you're adding and subtracting the amounts in those place values. And then you have to be able to learn how to, know how to regroup and move to the next place value. That's exactly what scientific notation is. It's exactly that. The power of 10 is telling us how to line up the place values. So this is where, your basic addition and subtraction meets decimal addition and subtraction meets exponents and powers of 10 and multiplication. So you probably, when you were back in a couple grades ago and you're learning all this stuff with decimals, and you're like, well, why do I need more than 2 place values? Because money only has 2 place values. And that's why, because now you're learning stuff that actually does things with more place values with scientific notation. And you never know, it could come in handy. You never know. You might think but you never know. And so if we make sure that the numbers have the same amount of place values, so the place values are equal with those powers of 10, then you can line them up. So here we go. Hang on tight. All right, so I can do a random addition problem, right? And I don't like, one of the things I don't like about PowerPoint and equation editor is you can't really do vertical equations. So if I add 100 plus 120, I get 220, because ones, tens, hundreds. Okay. Now, oops, I didn't write that very well. Now, if I'm going to rewrite it over here. I can rewrite 100 as 10 times 10. Now I'm going to keep this little exponent on here so that it looks like a power of 10. But I can rewrite this. So 10 times 10 to the power of 1, which is just 10, that equals 100. And I can rewrite 120, sorry. I can rewrite 120 as 12 times 10 to the power of 1, or 10. And that is still, that should say 120. I was just having issues today. I was going too fast. I should say 120. There you go. Okay, 120. Okay. And now, look, my place values are lined up. Ones, tens. So 22. And this is not an actual value. Remember, that's just instructions. So that doesn't change because it's just instructions. Times a power of 10 equals still 0, 2, 2. Okay. I know, it's pretty crazy. So as long as you have those place values, this is proof that adding and subtracting scientific notation, as long as you have the right place values with the powers of 10 and they're equal, that it works. Okay, so let's say we have numbers with different powers of 10, okay? Different powers of 10. We cannot just line them up and add them. That does not work. And this is why. If we lined them up, it would look like our place values are lined up. So we could line them up this way at that 0, but because those powers of 10 are not the same, this is actually lined up wrong. I know it looks right, but it's not, because remember, this is not the true value of the number. That is not the true value. That is just instructions. The true value is if I add 7 powers of 10, or add 7 place values times 7, 10 to the 7th power. So I can't just line these up because I don't have their true value. The only way to do it is to make sure that the true values are going to have the same place value. Like if you did it without scientific notation, that'd be like saying, look, if I have, and I'm going to write it vertically because this looks bad, I couldn't do it. But let's say we have 52 plus 91. Well, we would normally add it, if we went vertically, 52 plus 91, because we know these are the ones and these are the tens. Because they're already having the same place values. They are already in the same format. If we didn't have that, it would be like adding 52, but putting the 9 and the 1 here. Well, that doesn't make sense because the place values aren't lined up. You can't have ones plus ones and tens. I don't know what I'm trying to write there. That's ridiculous. You can't have that. It's not the same number. You can't just add a 0 here because that's a completely different number. You've added a place value and no one said to do that. So you can't just randomly do it because it's not the same value. So how do we do this? Well, we simply use the power of 10 or the scientific notation. Again, I cannot stress this enough. Scientific notation, the power of 10, even if it's not scientific notation, power of 10, is just instructions for place values. If you move that decimal, it doesn't change the value of the number if you account for it in the power of 10. That's like saying, look, I have 25 pennies. If you just give me 1/4, you haven't changed my value. You've accounted for that change. But if I have 30 pennies and you give me 1/4, then you've changed my value because you didn't account for it in the exchange. So this is what I mean. You don't have to do it all at once. For example, to get back to the original number, I would have to move my decimal 7 places to the right for the first number here, right? I would be adding 7 place values because I would be multiplying by 10 7 times. But I don't have to move it 7 times at once. I could move it 2 times and then move it 5 times later. I could move it 4 times and then move it the 3 other times later. You don't have to move them all at once. So let's say, look, this one is 6 place values. What if I just moved the decimal for this number 1 time? Then instead of 7, I've already used one. I already did one of those. So now I only have 6 left to move. I already added one of those place values. If I just multiply by 10, then I get 27 and a half. And I've used one of those powers of 10 and now to get the real value of my number, I only have to multiply by 6 tens because I've already used one of the 7 from my instructions. Because again, it doesn't change the value of my number. All it does is it moves me one step closer to following the full directions to get back to the original value. Like, what did this number start as? It started as this big number, and then I just did a bunch of stuff to it and wrote it differently, but it's still that number. It's just abbreviated. So this is how this looks. Okay. I've already proven. I'm just assuming you believe me. Well, I mean, I am right, but which is not always true. I am wrong a lot. If you've ever sat in on a help session with me and worked with me, you know that I am not right all the time, and I'm really open about that. Nobody's perfect. But I've gone through the steps to show you that 2.75 or 2 and 75 hundredths times 10 to the 7th is equivalent to 27 and 5 tenths times 10 to the 6th. So instead of writing my original expression where the place values are not the same, I can use up one of my powers of 10, and now my place values are identical. Now I can line up my numbers to add. Ready? Boom. Now when I line up my decimals, my place values are actually lined up, whereas before they weren't. That is not a good straight line. Let me try it this way. That's better. And so now I can say, look, 5 and 8, 13, regroup. 7 and 4 is 12, plus 1 is 11, sorry. 7 and 4 is 11, plus 1 is 12. Regroup. 2 plus 1 is 3. And remember, this is instructions. It's place value. And since they have the same place value, their sum will also have the same place value. Oops. So again, scientific notation, powers of 10, just instructions. Okay. So our answer is true, but usually we are told to rewrite our answer or write our answer in scientific notation. So we just have to now use our super special form and say, okay, well, the number I'm multiplying by the power of 10 has to be greater than or equal to 1, but less than 10. So see, I wrote it right here. I wrote 10. I knew what I was doing. I just didn't pay attention. So this number, in order to have it between 1 and 10 or 1 up to 10, the decimal has to be here because 3 and change meets that criteria. So what I've done is I have removed a place value. I had 3 tens, 2 ones, and 3 tenths. Okay, that's what I had. Okay. That's what I had. I took away a place value because now I no longer have tens. Now I have hundredths. And yes, I know I spelled that wrong, but I was running out of space. Now I have 300ths, 2/10ths, and 3/1. So I have taken away a place value. That means that to get back to my full value, I'll have to add an extra place value. So originally, I was going to have to add 6 place values, 10 to the 6th, to get my true value. But I rewrote it so that I took away a place value. That means to get to my true value, I have to go an extra space. I have to make sure I account for the place value I took away. Well, what is that? What is an extra place value? If I had 6 and I have to put an extra one, that's 7. So 6 plus 1 is 7. That's this extra place value right here. That's an arrow. There we go. That's the extra place value. And that's something that trips up a lot of people, is trying to get, because there's this, it's like, oh, I'm moving backwards, so I must subtract. I'm moving forwards, I must add. But that's not the case. You have to think of it in terms of directions. How do I get the true value? How many place values do I have to add or subtract to get to the true value of the number? And that's the power of 10. All right, so then I have that in there. So let's bring it all around. The original expression, 2 and 75 hundredths times 10 to the 7th plus 4 and 8 tenths times 10 to the 6th equals 3 and 23 hundredths times 10 to the 7th. And you'll notice if we had lined up our original without accounting for place value, we would have gotten something, adding, very, very different. And then, who knows what this would have been. Some people might have subtracted it. Some people might have added it. That is a completely different value. And why is that? Well, that's because if you look at these numbers in standard form, 1, 2, 3, 4, 5, 6, 7, and 1. So I'm going to have 6 place values and 1, 2. So there's going to be 4. 1, 2, 3, 4, 5, 6. See? That's thousands. That's millions. Because these, even though the decimal is here in the original problem, the place values aren't the same. And so you have to understand what the instructions are based on the power of 10. Now, the more you do of these, the easier it will be to see which one to adjust. A lot of times people just pick the first exponent, the first power of 10, and say, okay, I'm going to make this 7 into a 6 because it's the first one. But the more you do this, the easier it will be to see it, like quote unquote, see it in your head, to visualize and predict, oh, well, 6 is actually the smaller number. So I should actually make that into 7 because that's what the end is going to be. So that just takes practice, and there's nothing wrong. There's nothing wrong with doing it and having to convert it back at the end. It just takes a little extra time. So the more you practice, the better you'll be at saving yourself some time. Oops. I have got to clear. There we go. Now, we can't add or subtract unlike terms. We can't add or subtract different place values. They have to be the same. You add and subtract the same place values. You add and subtract like terms, but multiplying and dividing is a completely different beast. Okay? Multiplying and dividing are groups. So you can have groups of one version and tell me how many it makes in a different version. Like terms, units, place values, that doesn't matter when you're setting up multiplication and division problems. I mean, you have to account for it in your answer, but in terms of setting it up, you don't have to make sure that they're in the same form. So let's say we have, let's just review exponent rules. It's true that if we have the same base, oh, it says always written. I thought it said since scientific notation is not always written. I was thrown off. So scientific notation always has the same base. So we can apply exponent rules because they have the same base. So if we're multiplying powers of 10, we add the exponents. Therefore, when you multiply and divide, or divide powers of 10, anything really, scientific notation, please write out your steps. Please stop trying to do math in your head. Some people, that's really easy for them. But for most people, you have to write out your steps. You're going to make mistakes. Okay? And do one step, one thing per step, one change per line. Don't do like 10 changes at a time because because then you can't follow and check your work as easily. Now, multiplication is commutative, right? Multiplication order doesn't matter. So we can use this. So let's say we're multiplying scientific notation expressions. Now, they're not in the same place value, but again, that doesn't matter because when you're doing multiplication in general, you don't have to account for place value in the problem. You can do 327 times 41, and you don't have the same place values, but that's okay. I'm going to let me put a decimal in there because that one happens to line up. So 3 and 27/100 times 41. Well, you don't have to account for place value. You can write it as 3 and 27/100 times 41 because you're doing grouping. You're not doing totals. Okay, so you say I have one group of 7s. Well, that's 7. One group of 20. So that's 20. One group of 3. So that's 3. 4 groups of 7 is 28. 4 groups of 20 is 8, 80, 90, 100. So 8, 9, 10. 4 groups of 3 is 12, 13. So you don't have to line up place value. Can you? Yeah, but you just get a lot of extra place values. So instead, we account for the place value in the answer. And we say, look, this was hundredths, and this didn't have any extra place values. So my answer is going to be hundredths. And so place value, I can actually line these up, right? I can do 5.41 times 2.2. And it's okay that they don't have the same place values to line them up, that I don't know what those place values are going to correlate to. That's okay. So that means really what I'm doing is just multiplying all four terms. You see them in parentheses, but that just is done so that you can visualize the scientific terms, the notation terms. And the purpose of this is when you actually use this in context, the scientific notation expressions mean something. So this might be, like um, the 0.08, the 1.08 activity. This could be the distance from Mars to the sun, and this could be the distance from, I don't know, planet B, whatever it is. Okay. So that's why they're in parentheses. They're not in parentheses because you can't use the commutative property. They're in parentheses because that expression is actually means something. It's like tagged to a specific thing. And so that's why. But I can still use the commutative property. That doesn't go away. So I can then rearrange it so I have my constants together, and then I have my powers of 10 together. Well, now it becomes a very easy question because 5 and 41 hundredths times 2 and 2 tenths becomes 11.902. And then we add our exponents when we multiply the base, so 10 to the 6 plus 8, and that becomes 14. And now I've done my answer. But usually, again, it's going to tell us to write it in scientific notation. So all I have to do is say, look, my decimal can't be here because scientific notation says it can't be 10 or more. So I have to make sure that it ends up here. So what am I doing? I am taking away a place value. I had tens. I'm taking that tens away because now I'm going to only have ones. That means to get back to my original number, I can't just do 14. I have to do 14 and the extra one I just took away. So I'm actually going to have to move 15 spaces to show the true value of the number. There we go. So these are all equal to each other because they're all abbreviations for the true value of the numbers. Which, if you're curious, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Boom, 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 boom. Ta-da! Okay, so that's it. Scientific notation is an abbreviation. It's a number with instructions for the real value, the true value of the number. If you're adding and subtracting expressions in scientific notation, you just have to make sure that their place values are accounted for. And the way to do that is to rewrite the expressions so that their place values are the same, or their powers of 10 are the same, because then you're accounting for those place values. If you're multiplying or dividing, then all you have to do is use the commutative property and then multiply or divide your constants, your normal quote unquote numbers, and then use exponent rules for the powers of 10. And that's it. If it says write your answer in scientific notation, that just means you have to rewrite it in that super special format where you are multiplying your power of 10 by something that's greater than or equal to 1, but less than 10, and account for that in your power of 10. So you make sure you're saying, okay, well, now I have to move extra spaces to get back to the real value. or now I have to move less spaces to get back to the real value if you have moved because of division. Okay, and that's it. And now I am hoping that this was helpful. So that's the end of the live lesson. No one had any questions. So um, hopefully this was helpful. Scientific notation is it's one of those things that if you don't use it a lot, you kind of forget how to do it, and that's okay. And when you're trying to remember how to do it, or when you're learning it for the first time, it is pretty confusing. But the good news is if you really just think about it in terms of abbreviations with instructions based on place value, then it becomes a lot easier to remember the rules and what you're doing because there's some context to it. So I hope that you will join me again, or join me for the first time in another live lesson that is going over something you perhaps need information on. And have a wonderful rest of your day and week. And if you're on break, then rest of your break. And if it's the weekend for you, then weekend. And, just all sorts of fun. Stay safe, everybody. I will see you later. Bye bye.